Hello, ጤና ይስጥልን የማራኪ አካዳሚ ዩቲዩብ ቻናል ተከታታዮቻችን በዛሬው ፕሮግራም ካለፉት የመጀመሪያው ለሰን የቀጠለ ፕሮፖዚሽን ኤንድ ሎጂክ ያተኮሩ ሐሳቦችን አቀርብላችኋለሁ። እኔ ወንደሰን ነኝ። አብረን እንቆይ። ባለፈው ጊዜ እንዳየነው we have defined what a proposition is, what are the logical connectives ሚሉትን ሐሳቦች አይተናል። ዛሬ እንግዲህ በዋናነት more of audio በሆነ መልኩ ቴክስት ቡክን ተከትለን ቀጣይ ሐሳቦችን አብረን እናያለን። So you can do these exercises by yourself. So what is a compound or a complex proposition? So a proposition formed by joining two or more propositions by the logical connectives that we have seen earlier is called a compound statement or a complex statement or a proposition. So you can use, for example, P implies Q and R. For example, you have P and R are true and Q and S are false. Then what is the truth value of P and Q implies R or S? So first you have to follow the brackets, okay? Where there are brackets, first you do what is in the bracket. If there are no brackets, usually the precedence order is the conjunction and disjunction comes first, and then implication followed by implication. The negation is always the first operation to work with. Okay. So what are equivalent compound statements? Two compound statements P and Q are said to be equivalent if they have the same truth values for all possible combinations of truth values for the component propositions occurring in both P and Q. And in this case, we say P is equivalent to Q with this notation, P equivalent to Q. So let capital P and capital Q represent two compound propositions given by P implies Q and not Q implies not P. Note that the second compound statement is the contrapositive of the first. So contrapositives are equivalent statements. So you have P and Q, true, 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 false, false, true, false, false values. So corresponding not Q and not P are given here. So P implies Q has truth values true, false, true, true. Not Q implies not P has truth values true, false, true, true. So both are true in the first case. In the second case, both are false. In the third case, both are true. In the fourth case, both are true. Hence, the compound statements P and Q are equivalent. And that is shown using columns 5 and 6 in this table, okay? So, other issues, what is the converse, the inverse, and contrapositive of an implication statement? So, the converse of the statement P implies Q is Q implies P. The inverse of P implies Q is not P implies not Q. And the contrapositive is not Q implies not P. So what is interesting is especially the contrapositive of the statement. So the contrapositive of an implication statement is always equivalent to the original statement. That means P is a sufficient condition for Q. P implies Q means P is a sufficient condition for Q, right? So Q is a necessary condition for P. That means if not Q, then not P, okay? P implies Q means if not Q, then not P, okay? So, for example, you have examples here. If Kadis lives in Addis Ababa, then she lives in Ethiopia, okay? What is the converse? The converse. If Kadis lives in Ethiopia, then she lives in Addis Ababa, okay? If P implies Q, the converse is Q implies P. The contrapositive, if Kadis does not live in Ethiopia, then she does not live in Addis Ababa because someone who is not in Ethiopia cannot be in Addis Ababa. Okay, obviously, Addis is a subset of the bigger set Ethiopia. The inverse is if Kadis does not live in Addis, then she does not live in Ethiopia. As you can see, somebody who is not living in Addis may be living in some other city in Ethiopia. So it's not logical. Okay, these are some of the identity laws. Equivalent statements. So the first one is the idempotent laws. P or P is equivalent to P. P and P is equivalent to P because in both cases, both are true or both are false. So the result is the same. If two statements are true, whether they are joined by conjunction or disjunction, the result is the same. If both are false, the same. Conjunction and disjunction are both commutative. They are both associative. and one is distributive over the other. Conjunction is distributive over the disjunction, and disjunction is distributive over the conjunction. The De Morgan's law, the negation of P and Q is not P or not Q. The negation of P or Q is not P and not Q. So when you do the negation, you apply the negation on both propositions, but the conjunction will be converted into the disjunction and the vice versa. And the law of contrapositive, P implies Q is equivalent to not Q implies not P. So, okay, so the complement law, twice negation gives the original proposition. The other interesting issues are tautology and contradiction. If a statement is always true, regardless of the truth value of the component propositions, we call it a tautology. And the other extreme is, if it's always false, regardless of the truth value of the component propositions, we call it a contradiction, okay? If it's somewhere between the two, that means if sometimes true and sometimes false, a proposition that's neither tautology nor a contradiction is referred as a contingency, okay? These are just terminologies. You can see, for example, this one, P or not P, and P and not P are both, P or not P is a tautology, P and not P is a contradiction, because P and not P means one is true, the other is false. So by the disjunction, it's a tautology. By the conjunction, it's a contradiction. So to show whether a given proposition, a compound proposition is a tautology or a contradiction, or neither of the two, a contingency, one way is to use a truth table. You can use a truth table and use the all possible combinations of true and false values for the component propositions, and then you can depict easily using the truth table. Otherwise, you can also show using case by case, okay? Case by case, when the component propositions assume a true value and the others would have true and false combinations. But I think truth value is more convenient, okay? Because truth value itself is case by case, considering the true and false values, all possible combinations. If you have two component propositions, how many possible true and false values you will have? To the power of n, which is 4. If you have 3 component propositions, how many true and false combinations? 2 power 3, which is 8. So in the same way, you can do for higher number of component propositions. So you have exercises here. You are requested to go through these exercises for the to prepare yourself for the mid and final exams. Okay. So today, one more thing is about open propositions and quantifiers. So what are open propositions? And what is a quantifier? In fact, an open proposition is a statement, actually any sentence which contains variables, 2 or more variables, as you can see here. So that contains 1 or more variables whose truth value depends on the truth values of, on the value assigned for the variables. So we represent an open statement using capital letters followed by variables, P of Q, P of X, Q of X, R of X, Y, etc. For example, X is a day before Sunday. This is an open proposition. Why? Because X is a variable. We don't know what X is. If X is a day before Sunday, so if X is Saturday, it will be a true proposition. If X is any other day, it's a false proposition. So it depends on the variable X. Such statements are said to be open propositions or open statements. Okay. What are some of the features of these open propositions? 2 open propositions, P and Q, P of X and Q of X, are said to be equivalent if and only if they assume the same truth value for the same variable, for the same value of the variable. Okay, for all values A, if P of A is equal to Q of A, in the sense that one is true, if one is true, the other is true. This equality is in terms of truth value. Okay, if one is false, the other is false. It's not a number. Okay, equality is the sense of truth value. So note that if the universal set is specified, then P of X and Q of X are equivalent if and only if P of A is equal to Q of A. That means one is true, the other is true. If one is false, the other is false for all elements in the universal set. Okay, you can see this example. P of X is X squared minus 1 is 0. Q of X is absolute value of X is greater than or equal to 1. So the universal set contains only 4 numbers here. So for all these numbers, P of X and Q of X assume the same truth value. If P of X is true, Q of X is also true. If P of X is false, Q of X is also false. So they are equivalent. Okay, they are equivalent. You can see that by yourself. So let U be a universal set. An open proposition P of X is a tautology. Another issue is, when is an open proposition a tautology or a contradiction? So an open proposition is a tautology if and only if the truth value for all value of the variable is true. If it's always true for all elements in the universal set. And the other extreme, if it's always false for all elements in the universal set, then such an open proposition is said to be a contradiction. Okay? For example, consider this: r of x equal to x squared greater than or equal to 0. So we know that for all elements in the universal set, where the universal set is a set of real numbers, r of x squared greater than or equal to 0 is tautology. Why is it a tautology? Because for all x's, this is always true. This is always true. Okay. Okay. So another way of looking at open propositions is by quantifying these open propositions. An open proposition contains one or more variables. So by quantifying, we mean a universal quantifier or an existential quantifier. By saying every x satisfies this property, or some x satisfies this property. Okay, so a universal quantifier with a notation for all x, as you can see here. An existential quantifier, there exists x, that means at least one x in the universal set satisfying the property P. So we quantify statement means we declare that that property is satisfied for every x in the universal set, or for some x, for at least one x. That's called existential quantifier. Okay. So we show that the property is satisfied for all x universal quantifier. We show that this for all x p of x is false if we can show a counterexample. Okay, that makes the statement false, at least one. Then we say the statement is false, and that value is said to be a counterexample. Whereas the existential quantifier, there exists x p of x, is false if we can not find a single value that satisfies the property P. Okay, that means if the existential quantifier is true if we can present at least one example. Okay, that satisfies the property P. Okay, here are some of the examples. What are some of the relationships between the existential and the universal quantifiers when we negate the statement? You can see it here. The negation of for all x p of x. Okay, once an open proposition is quantified, for all x p of x is a proposition. It's a quantified proposition. So the negation of for all x p of x is equivalent to the existential quantifier. There exists x not of p of x. Okay, the negation of p of x. That means all elements do not satisfy this property, means there are elements that satisfy the negation of that property. And in the same way, the negation of there exists x p of x is equivalent to for all x negation of p of x. That means the negation of some x satisfies the property means every x satisfies the negation of p. Okay, if there is no x that satisfies the property P, that means every element is satisfying the negation of the property. Okay, so here are some of the examples. Okay, and the other issue is the other thing is, I'm sorry, and the other thing is when we have two variables. Okay, when you have two variables, we can quantify still an open proposition containing two variables p of x, y, but the order of the way we quantify these open propositions is something that you will be very careful. So for all x, for all y, p of y means for all x, and for all y, the relation p of x, y holds. Okay, for every x, for every y. There exists x, there exists y, p of x, y means there is at least one x and there is at least one y that satisfies the property. How about these two, the last two? For all x, there exists y, means for every x, there is a y satisfying this property. Whereas there exists x for all y means there is an x which stands for every y in the relation p of x, y. That means this one is very sensitive. You should be very careful at. There exists x for all y means there is one x, okay? There is an existing value x naught that satisfies the property p with all y's, okay? For example, let's have a look at this example before we wind up this session. Suppose p of x, y is x plus y equal to 5, okay? P of x, y, x plus y equal to 5. So there exists x, there exists y, p of x, y means there is at least one x, there is at least one y. Our universal set is a set of integers. Among the integers, there is at least one integer, there is at least another integer that the sum of which is 5. So this is true. You can take 2 and 3, you can take 0 and 5, you can take any, 4 and 1. Okay. Another is there exists x for all y, satisfying the property p. That means, can you have a single value of x where for every y that x plus y is 5, this cannot be, because if x is fixed, y would also be fixed. It cannot be for all y, so this is false. The third is for all x there exists y, satisfying the property p of x. For all x, that means by changing x, you get a corresponding y, that the sum of which is 5. Yes, it's possible. Okay, so it's true. The last one, for all x and for all y, the property p of x is satisfied. That's not true. If you take random x and random y, then for example, if x is 10 and y is 10, 10 plus 10 is 20, it's not 5. So for all x and for all y, it's not true. So this way, you can decide whether a quantified statement is true or false. So these are more interesting examples. And you have exercises on page 19 and 20. Okay, so in our next session, we'll see about arguments and validity. Okay, so I advise you to go through the textbook, through the examples and exercises before you go and refer other materials. Okay, so this was all for today. Thank you very much. See you next time. Bye-bye.